I may mention some things that are not in the book. If you notice that I mentioned something that's not in the book, I wouldn't worry about it. I won't hold you to it. But just things I think you should know and are useful. When we talk about equation of a line, we're talking about an equation in the form ax plus by equals c. But this is not my favorite form of this equation. My favorite form of this equation, because it's so much more useful, is the slope-intercept form. Which is y equals mx plus b, and being the slope, and b being the y-intercept. In particular, you should remember the slope m is the change in y, delta y over delta x. So when we want to graph something like this, we can first start with wherever the y-intercept is. All right, so this is my b. And then from this point we can move delta x in the x direction and delta y in the y direction, and we can always draw the line that way. In particular, this line that I just drew, the slope is going from left to right upward, so the slope is greater than 0. Instead, I have a line where it's going from left to right downwards, it's downhill, and I know the slope is going to be less than 0. If the slope happens to be 0, then I get a particular version of the line where all the y's are the same. It's a constant. So the equation of this line would be y equals some constant here, or if you like, b, the intercept. And then there's one more possibility, which is I could have a line which is perfectly vertical, and here the slope is what? Well, change in y from one point to the next, or change in x. Well, the change in x is 0. Divided by 0, it's undefined. So this is an undefined slope. It's a perfectly good line. We could say x equals some other constant, say d. Okay, so that's graphing lines. Come back to this. So what do we do with lines all the time in algebra? Well, we get two of them, right? We'll get like cx plus dy equals e, and we want to find their solution, right? So let's think about what that means. What's the solution of two equations? Well, it's a point x and y, where if I plug in x and y, both of these equalities are satisfied. Another way to think of it is graph the two lines, hopefully they intersect somewhere, and that xy point, I mean, on this line, say this line is associated with the first equation, so all these points satisfy this line. The second equation has another line, all these points satisfy it. So the one point where they cross is the solution. We're going to look at how you find that solution, but before we do, we want to just take a look at the two gotcha cases, right? What if I have two lines, but they're parallel? They're never going to intersect, there'll be no solution. Now, one way you can find this is you can try and solve the way we're going to show you, and something will happen that will alert you. But there's a really simple way to see that we have two parallel lines. Does anyone remember what that is? Same slope. Right. That's why I like this form here, y equals mx plus b. Because if I look at the two equations in this form, I'll immediately see their slopes are the same. Now, if their slopes are the same, it is possible that they don't intersect. There's one other possibility, is they could be the same line, in which case every point on the line is a solution. The solution is the entire line. Okay, those are the two gotcha possibilities. All right, let's take a look at so this should be really easy. Everybody should know this. If you're not, you should come office hours today or Wednesday. But that also might mean it's getting a little boring. So I'm going to do two things here to make it a little less boring. I'm going to pick up the pace. And then I'm going to tell you, I have some stories about this that good stories. Okay, so let's do an example. Let's start with x minus y equals 4 and 2x plus y equals 8. Now, I think just about every math book I've ever seen tells you one way to solve this is to graph it. I think that's a terrible way to try and solve one of these. To begin with, it takes a lot of drawing, it may not be accurate, it's not very mathematical. But if you like that method, you can try it. It's only going to work well if you have nice numbers and a nice solution. So we're going to do it algebraically. The two main ways you learn to do this are substitution and elimination, both of which I will demonstrate. For substitution, I need one of these equations in the form variable equals stuff. So I'm going to add y to both sides here, and I'm going to get x equals y plus 4. That's, x equals stuff. I then take this equation, plug it in here. We don't call this elimination, we call it substitution, but it's eliminating the x. So I have 2 times y plus 4 plus y equals 8. This is just an equation and one unknown. I know how to do that. 3y plus 8 equals 8. Is that right? 2y plus y. 2y plus y. Okay, so 3y equals 0 or y equals 0. That tells me the y value of the solution, I still need the x. Well, I get that by plugging y back in here. I can plug it into either equation, it should work. X minus 0 equals 4, so x equals 4, or my solution should be 4, 0. I can try plugging it back in here. 2 times 4 plus 0 equals 8. So that's the right answer. Okay, that's substitution. With elimination, we look at these two equations and we say we want to either add them together or subtract them in such a way that we eliminate a variable. Now sometimes to do that you have to multiply one of the equations by a constant. Like if we wanted to eliminate the x, we have a 2x here and an x here, we could multiply this by 2x, subtract and get rid of the x. But we never want to do more work than we have to. I mean, this is already set up here very nicely. We've got a y and a minus y. If we add them, let's just do that. X minus y equals 4. 2x plus y equals 8. So let's add them. 3x plus, well, we got rid of the y, equals 12. We divide by 3, x equals 4. Looks like we're on the right track. Again, to get the y value, I just can put x back into either of these equations. So if I say 4 minus y equals 4, I'm going to find out that y equals 0 again. All right. I want to show you one other method that some of you may have run into. It's called Cramer's rule. Has anyone seen Cramer's rule? That's bad. Okay. Well, has anyone here ever done any work with matrices? Good. Okay. All right, well, what you need to know about Cramer's rule for matrices is something called the determinant. It's a big fancy word, but it's really an easy idea. You had a matrix. A matrix is just an object with more than one number in it, in rows and columns. And we're only interested in a 2x2 matrix for our purposes. So the determinant of this matrix we figure by doing the following. We multiply this diagonal, AD, and we subtract this diagonal, CB. And that's our determinant. Right, why did I bring that up? Well, Cramer's rule is a formula for the solution. It says x equals, the solution is one determinant over another. Okay, I'm going to show you how you get the bottom determinant first, because that's the easy one. I put my equation in this form, ax plus y equals c, and so forth. And then I just look at the numbers here. X, the coefficient of x is 1. Coefficient of 2x here is 2. Coefficient of y here is minus 1. And the coefficient of y here is y. So that's the determinant of the denominator. For y, it's going to be exactly the same, which means when I figure out y, I want to do it this way, I can use the result here. How do I get the upper determinant? Well, because this is x, I'm going to substitute for the x's this. 4 and 8, minus 1 and 1 again. And for the y, same idea, I'm going to substitute this in for the y's. It's going to be 1, 2, and then 4, 8. All right, well, let's figure out these determinants here. So this is going to be 1 times 1 minus 2 times negative 1, that's plus 2. Here I'm going to get 4 times 1 minus negative 8 times 1, which is plus 8. So I get 12 over 3 or 4, which is 4.
Excuse me.
Yes?
Just repeat how you got the numerator again.
Repeat how I got what?
The numerator matrix.
That's the hard part.
Yeah.
Okay. Let me do it a different way. I just did. Just write down the same as the denominator, right? You know where that came from, right? Comes from these 4 numbers. Now for x, I look at where the x's are. They're over here. And I substitute these 2 numbers, 4 and 8. For the y, I look where the y's are, and I put those same numbers in here. Okay, 8 minus 8 is 0, so y is just 0 again. Now, let me tell you 2 really good things about Kramer's rule. Well, I only have one good thing, and I have a story. Let's say I wasn't dealing with ax plus by, I was dealing with ax plus by plus cz equals e. And maybe I need better notation here. How about ax plus ay plus az z equals a naught. Well, I can't solve one equation with 3 unknowns, but maybe I have another equation and a third one, right? See where notation kind of helps. I mean, if I had to say A, B, C, D, E, F, G, H, start getting lost. Well, it turns out Kramer's rule looks pretty much the same. My x is just, the numerator is going to be ax, ay, az, bx, by, bz, cx, dy, cz. My numerator, well, again, I'm just going to substitute these values in for the x. So a naught, b naught, c naught, ay, by, cy, az, bz, cz. Now, that's the simple part. Complicated part is how do you find the determinant of a 3 by 3 or 4 by 4, 5 by 5. This works with any large number. Well, I'm not going to cover that today. But you can see if you're like a computer programmer and you're faced with solving a lot of these equations, it's better to have a formula, right? You just plug your formula into your computer or you have it figured out. Maybe you even have a determinant function. Would be nice. And that solves your problem. So now we just jumped from 2 by 2s to n by n, right? N equations and n unknowns. Now we know how to solve it, at least theoretically. Okay. So this is just about lines, or in the 3 by 3 case, what I'm dealing with is I like 3 planes, you know, just geometrically. I guess I need to break out the colors, right? So I have these two planes, and they needed a line, and I have some other plane, and I'm not any good at 3D, so 3 planes needed a point, hopefully. Some parallel planes. That's great. So what? This just seems like some kind of, you know, hokey thing we learn in math. Maybe someday in economics you're going to see a supply and demand curve, and you know, the supply demand, you know, the amount of supply depends on the price, so the supply will go up with the price, but the demand will go down with the price. Right? People will buy less because it's more expensive, and then somewhere in the middle there's some sweet spot, as if these things were actually straight lines. Economists would like to think that, but they're not really. You can do that. So I'm going to tell you a story. I know some of you are interested in computer programming, and I've done a lot of that. And one day I got called by a company. Does anyone here know what LASIK is? Mm-hmm. Has anyone had LASIK? You're not going to like what I'm going to say. Don't do it! Don't do it! I learned all this from the laser guys. When they laser your eye, they tell me it never fully heals. All right, it's too late. They probably did a good job. LASIK is a machine which they have a box with a laser in it. Shoots a laser beam out, and you're kind of sitting over here, you know, smiling, I guess, but looking up. You're on a table. There's a stick figure on the side, and there's a mirror here that it moves around, right? And it moves the laser, and then there's some fixed mirrors. And then they just focus it right on your eye. So they cut a little pattern in your eye. And they had a problem with this machine because it's all run by software, and the guys who wrote the software left. And they thought, we don't understand this. We need a mathematician. So I said, I'm a mathematician and a programmer. I said, great. Come help us figure out what this program is doing. So what is this program doing? Well, the thing is, you know, these mirrors, they're all in these arms that can move. So they have to adjust it. And every time they adjust it, it gets a little out of whack. So to align it, once, you know, they move the arm where it is, what they do is they shine the laser on a target, and they shine 4 points. And then they look at, you know, where those 4 points are. You know, maybe they're a little out of whack here. And then they compensate for it. And that's where the problem was, the code that did that. They look at this code and they know what the heck to make of it. So I'm looking at this code, and it kind of looks like this. It looks like ax minus by over ac minus d, something like this. And I'm staring at this and going, wait a minute. That's Kramer's rule. They hired me because, I have a master's degree in mathematics, to do high school algebra. Now, I say that someday you, who are interested in computer science, might someday walk into a job and They have no idea what's going on, and suddenly find that this stuff actually it shows up. Okay, that's my story. Let's get on with the lines. Any questions on any of this so far? Okay. If you don't remember Kramer's rule and you ever need it, just look it up. You don't really need to. Memorize it. Okay, so what kind of problems are we going to solve with lines? The first and obvious one is, what if I have 2 points and I want to know the equation of the line going through them? This is where my slope-intercept form comes in really handy. I know the slope is, for any 2 points, is delta y, delta x, which is just, we'll call this y2 minus y1, or x2 minus x1. So in this particular problem, I can choose either of these as 0.1 or 2. It doesn't matter. So let's make this y2 and x2 and x1. Let's try again. It's Monday. x2, y2, x1, y1. So y2 minus y1 is 5 minus 1. x2 minus x1 is 8 minus 2 is 4 over 6, or 2/3. That's my m. So now I know my equation is y equals 2/3 x plus b. I just need to find b. Well, again, I have 2 points on the line. I can plug either of them in and find out. Let's try using 2. So y equals 2 times 2/3 is 4/3 plus b. Oh, we know what y is, it's 1. So I subtract 4/3 from both sides. 1 minus 4/3 is minus 1/3. So now I know my equation is y equals 2/3 x minus 1/3. And you can check both of these points will be on that line. If you need to put it into another form, you could multiply both sides by 3 and then subtract 2x, and you get minus 2x plus 3y equals minus 1. Right? If you want it in a plus b equals c, ax plus bx equals c form. Okay, that's how you find the equation of a line given 2 points. There is an alternate formula you can use that I find hard to remember, so I don't try and remember it. But if you want it, you could remember that y minus y1 equals m times x minus x1. We already know the slope here is 2/3, so y minus, let's pick, say y1 is 1, equals 2/3 x minus x1, 2. And if we rearrange this, we'll see it's the same equation. If you like the point slope form. Okay. We already talked about vertical and horizontal lines. The line is horizontal when it's in the form just y equals c, there's no x. It's horizontal. And x equals some constant, that's a vertical line. These these are going to be a special case for the next issue. The next issue is, how do we know lines are parallel or they are perpendicular? Do we know perpendicular? Perpendicular at right angles. It's a little symbol for perpendicular. Sometimes this is used as a symbol for parallel. Well, parallel is easy. If you look at two lines, you look at their slopes. Slopes are the same, they're parallel. Or possibly the same line. The perpendicular, oh, pause. What if you have something like this? Well, if one of the lines is horizontal, in other words, this y equals a constant, you know the other line is parallel because it's horizontal and a constant. Some other constant. It's a vertical line, well, both of them would be in this form, x equals. They both have undefined slopes. So if both slopes are undefined, they're parallel. If both slopes are 0, they're parallel. Otherwise, you have to actually calculate the slope. Perpendicular is a little more complicated. We're not going to derive this. Hopefully you've seen it. If you come to my office hours, I'll be happy to show you. But slopes that are perpendicular are negative reciprocals. You got to get both. You got to get negative and reciprocal. So let's look at some examples of negative reciprocals. All right, let's say 2. Negative reciprocal would be negative 1/2. Okay, that's easy. Reciprocal of, say, 3/4. Okay, negative 4/3. This sounds so easy, yet so many students will take a quiz and they'll have a reciprocal or negative, not both. Okay, how about 1? What's the negative reciprocal of 1? Negative 1. What's the negative reciprocal of 0?
It's 47.
That's not a bad answer, given I like humor in the classroom. Well, the reciprocal of 0 is undefined, right? But remember, if the slope is 0, it's a horizontal line, so perpendicular to a horizontal would be undefined, would be a vertical line, right? I'll just say undefined. Okay, well, surely we have a problem related to this. So here would be a typical problem. I start with the equation 4x plus 6y plus 5 equals 0. And I want to know the equation of a line. I'm just going to do the perpendicular one since that's the fun one. I want to find a line perpendicular to this that goes through point 0, 0. So, you know, I have this line, I don't really know what it looks like. Oh, that's not going to work. Oh, yeah, it is going to work. And I want a line that goes through 0, 0, but is perpendicular at right angles. So the equation of this line is what I want to know. Okay, the first thing to do, we want to know the slope of this, so we want to put it into slope-intercept form. So let's solve for y. 6y equals negative 4x minus 5. Y equals negative 4/6 or negative 2/3 x minus 5/6. Okay, what is the negative reciprocal of minus 2/3? 3/2. Right? So I know the line I'm looking for is y equals the new slope, 3/2 x plus b. So b is yet. But I have a point on this line, 0, 0. So I plug in 0, 0 equals 0 plus b, so b equals 0. So y equals 3/2 x, that's the equation of the perpendicular through 0, 0, perpendicular to this line. You can do the same thing with the parallel, except instead of finding the negative reciprocal, you just keep the slope the same. Okay. Another story. Why would you care about this stuff? Again, I'm appealing to you, those of you who maybe are thinking of career with computers, writing software, doing neat stuff. About 10 years ago, I started communicating with this guy. I was on a board, boards, talked about computer stuff. We were using a system called Unix, which is unimportant. Software they used to use in BlackBerries for a little while. Now, it's probably in some of your cars if you have a car, or if you get a car. Anyway, this guy was in Arizona, and he was doing something, he was involved with something called the Grand DARPA Challenge. By the way, it's going to take me a few minutes to get to the y equals mx plus b stuff. Does anyone know what the Grand DARPA Challenge was? Okay. Well, the U.S. government was fighting this war in Iraq, and they kept getting their equipment blown up. I thought, wouldn't it be great if we had trucks that didn't need drivers? Just send the trucks wherever they're going, and nobody could get hurt if they blow them up. So they put on a contest. I mean, this sounds like stupid today, because Google cars are driving around now. They don't need drivers, right, until it hits somebody. But they put out this contest to see who could come up with a car that would drive itself. And I was talking to this guy who lived in Arizona who was going to enter it. He was an amateur. He had a lot of money and he had a lot of heart. But he was an amateur, and he had no idea what he was doing. He just had a bunch of engineers and were building the vehicle. He didn't know anything about software. And he was trying to get his software going, and I said, no, I'm not doing anything. I'll come down and join you. So I get down there, and he's got this old 1940s, it's an ambulance, military ambulance. And in the back of it, he's got all these computers. He's got all this, hardware to hook up to the steering wheel. He's got something to control the gas pedal. And he's got these cameras mounted on here. But he doesn't know what to do with them. So, first thing I had to do was figure out how to get the image, I wasn't that hard. We have a pine tree here, and we have a house, and we have a road going by. It wasn't hard to get a picture of this. But honestly, I don't know anything about this stuff. I don't know anything about image processing, how to drive a car. But I did have a book which told me how to create an inverted image. It's like you take an image of something, well, you get a picture. But basically, it just kind of extracts the lines, right? So the next time you're in a car on the highway, look out the front, kind of just take all the other distractions out of your head, and what do you see? You see lines at different angles, right? And I could get an image with the two lines on either side of the road. And I thought, you know, if the lines are like this, well, they're going to bend in a little because of perspective. If the angles are the same, then that's fine. I want to go straight, right? But if the angle up ahead is kind of a little off to the right, what? It means I got to turn the wheel, right? So what did I need to know? I needed to know the slope of these lines. So I'm just saying, you know, as simple and stupid as, you know, this algebra, finding these lines, it actually has practical applications. I mean, I wrote some software, and we had the vehicle turning the steering wheel to keep it on the road. Yes, Ian?
Why wouldn't they just use, like, remote control cars?
Well, okay, so why wouldn't the government do that? I don't know. There might have been a good reason, but the Grand DARPA challenge was a car, you just say go, it had to go from point A to point B. This was the second competition. The first one just had to go from point A to B. The second competition, you had to drive on streets and stop for pedestrians. We never got this going. I mean, we got it to drive, but we didn't get not hit pedestrians or things. It had a big red button on the side where you could run up and hit the button and it would stop. Because we were pretty sure it was going to hit somebody otherwise. Anyway, okay. I think that's it for today. We have a few more minutes if anyone wants to stick around and ask questions about homework. Happy to try and answer.
Yeah, we can.